I'm Sean, with Adrian here. We're going to be talking about the Strategic Spatial Energy Plan. So I'm in NESO, Adrian's in Baringa. So I'm going to start off by just giving a bit of a background in terms of what the SSEP is and also who we are in terms of NESO and our new responsibilities. Great, so starts off, so we were established as NESO, as a public body, around 18 months ago. And when we were established, we were given some new responsibilities, which are shown here on the right-hand side. So there's a bit of a split here between your sort of planning and operational activities. And then we've got data and AI, seems to be the theme of the day, sort of wrapping around all of these activities, helping to facilitate digitalization. So, yeah, we work very closely with government, Ofgem, and other parties to ensure a coordinated strategy moving forward for the energy landscape. And we help to shape the future to meet different policy ambitions. So that's key of what we're trying to do today and into the future. We're going to be talking more around the planning side of these activities today, essentially the strategic planning activity, so which leads me on to the SSEP, or the Strategic Spatial Energy Plan. So in 2023, the concept of a Strategic Spatial Energy Plan was first introduced, and this was in a report produced by the Electricity Network Commissioner. Later that year, the UK's Transition Acceleration Action Plan set out how an SSEP or a plan like this would be delivered. And in October 2024, we were co-commissioned by the UK, Scottish and Welsh Government to deliver the first SSEP. So this is all as part of a wider set of activities to deliver Clean Power 2030, as well as getting us to net zero by 2050. So the aim of the SSEP is to accelerate clean, affordable and secure energy. The SSEP will have status in planning, so another aim is to really give that certainty to the market and to different stakeholders, and to have those early discussions with supply chains and just early discussions to provide that certainty to the market. What we're going to be outputting is zonal optimal capacities for different technology types for hydrogen and electricity. What the SSEP is not doing is looking at detailed locations of where different plants are going to be. It's at that zonal level that we're going to be outputting. The sort of more detailed breakdown of exact locations will be looked at in further processes along the pipeline. Great. So a bit of like wider context. There's lots of things happening in NESO, as I showed in a couple of slides before. The three here are sort of the core plans that are happening right now, with the SSEP sitting at the top, given that top-down approach to come up with a strategic plan. We've got the CSNP, or the Centralized Strategic Network Plan, which looks at your network recommendations and plan for network solutions into the future. So they're looking at detailed projects, real projects, of how we deliver requirements set out in the SSEP. So in the SSEP, we do look at transition requirements, but it's fairly high level. And the CSNP looks at real projects, how we would deliver that. We've got the Regional Energy Strategic Planner role. So this is taking more of a bottom-up approach compared to the SSEP top-down approach. So it's really important here that we get a view from both sides and they do merge together. This is cycle one of both the SSEP and the RESP, so it's difficult right now, as you can imagine, they're brand new processes, but hopefully as we go through more cycles, so 3 years is the SSEP cycle, it should integrate a bit easier. So you've got more sort of activities on the bottom here. The SSEP is generally feeding into most, if not all, of these. And again, it's going to really give that certainty that feeds into the rest of the projects as an input. Great. So what is, I guess, the aim of the SSEP and what should it mean for the industry? So it should give clarity and certainty on government direction for the energy system. Again, as I mentioned, that top-down, bottom-up approach, the alignment with local decision-making, support through consenting. The SSEP will have a status in planning, so that should make consenting and planning easier for developers. Better coordination with network planning. So again, we are looking at those high-level network solutions and requirements into the future up to 2050. Alignment of regulation and support schemes. So again, we're feeding into lots of projects here. And as I mentioned before, site-specific choices are going to remain with the industry and the market and local actors. We're outputting a zonal capacity for different technology types. Great. So I'm not going to go into the pathways in a lot of detail, but just wanted to touch on what we've been playing around in the model when we were in our exploratory modeling phase. So in PLEXOS, these are the different levers we've been pulling to come up with, I guess, different possible futures out to 2050. So we've got the base run, so this is what the model really wants to do. This is lowest cost or economically optimal solution. It's one thing in the model spitting out, but you have to take a step back and think, is this realistic in terms of what the model's building? So this is really the base run is optimal in terms of economically optimal, but is it deliverable? Maybe no. Leads us to the sort of second theme, reduced land impact. So this is really limited in PLEXOS with your sort of max build. For the low power density technology types, if you set a max build for them, how does it impact the rest of your pathways? So again, reducing the impact on land for onshore technologies. Higher low carbon dispatchable power is another lever we pull with. So in PLEXOS, these are minimum builds that we put into the model. So if something is maybe fairly expensive or doesn't get built naturally, we will force PLEXOS to do that and review the impact. Lower reliance on nascent technologies. So we don't want to put all of our eggs in one basket. If the model decided to put 50, 60, 70% of the capacity into one technology type that we're not 100% confident in the inputs, we need to understand what that means and what would it build instead for those more, for the technologies that are on the system today. And we've also played around with lower reliance on unabated gas just to see what happens there. I'm going to pass on to Adrian.
Thank you, Sean. So I'm just going to be talking about how we've actually gone about the modeling with NESO for the SSEP. So the SSEP uses a combination of both economic and geospatial modeling to determine where, what, and when to build power and hydrogen infrastructure in Great Britain. So the economic modeling is simulating operation and expansion from a cost perspective, trying to minimize costs for the system. The geospatial is looking at land and sea use, looking at the exclusions, the constraints, and opportunities for developing infrastructure in different parts of the country. And we use these in combination to achieve a balance of pathways. Sean and I are representing the economic modeling team, so we'll talk more about that, but we'll touch on the geospatial as well. So the economic model, these are the key inputs to it. So there's inputs such as the geospatial, so this is telling us what we can build where. There's a baseline, so we're starting the model from 2031, so that's our starting point, and we're going out to 2050. There are deliverability constraints, which is looking at the supply chain, how quickly can we build infrastructure on a GB-wide basis. We then have demand projections. Now this, as Sean said, this study was commissioned by government, by the UK, Welsh and Scottish government, so those stakeholders are feeding in their views in terms of the evolution of power and hydrogen demand, and this would include electrification of transport, of heat pumps, etc. All of that is fed in as detailed demand projections out to 2050. We also have the government's views on macroeconomic inputs such as commodity prices, carbon prices, interest rates, etc. Costs, obviously a key component, the cost of the various technologies that we're looking to optimize, and then various policy levers. We've got the net zero targets, but there could be more specific targets from a UK or devolved government perspective. So all of those feed into the model, and then we iterate with with our geospatial colleagues, as I'll go on to in the following slides, who are then looking at the outputs of the model and then evaluating those from a land and sea use perspective, and also conducting environmental assessments as well. So probably no surprise, given where we are today, to learn that behind the economic model sits PLEXOS. So we're using PLEXOS in its capacity expansion mode to develop the co-optimized view of a least cost expansion for GB under a net zero scenario to 2050. And we're doing that across multiple technologies. So we're looking at power generation, renewables, nuclear, low carbon dispatchable, unabated gas, storage, batteries, longer duration storage technologies. We're looking at network reinforcement. We're looking at interconnector expansion to other countries. We're looking at hydrogen production, blue and green. We're looking at hydrogen pipelines, hydrogen trucking, hydrogen storage facilities. All of that is being co-optimized out for 20 years to 2050. So it's a very large problem that we're trying to solve. We're doing that on a spatial basis. So in the PLEXOS economic model, we have 17 onshore zones for Great Britain that represent the major transmission constraint boundaries for electricity and hydrogen to some extent. We also have 19 different marine zones offshore, which could connect to different onshore locations. We also model, as I said, the interconnection to other countries, and we can expand that. So there are 7 countries to which we can build additional interconnection from any one of our 17 zones. So that's the spatial problem we're trying to solve, and then we're trying to solve this out for 20 years with an hourly view of system dynamics. We also have over 30 years of historical climate data there on a pan-European basis for wind and solar and demand, looking at things like Dunkelflauters to make sure that we're keeping an eye on security of supply as well as the economics. So that's the problem we're trying to solve and asking PLEXOS to solve for us. I will briefly try and touch on the geospatial as well. So Sean and I on the economic side, we're working with 17 onshore zones, plus the 19 offshore. Our colleagues on the geospatial modeling side, they are dividing Great Britain into little hexagons, which apparently tessellate well, and they've got something like 650,000 hexagons for the country. And for each of those hexagons, they're evaluating the suitability of that land or sea space for infrastructure development. So that could include technology-specific requirements. If it's, say, a nuclear site, then you might need some access to cooling water. Hydro pump storage would need particular geographic terrain. Salt caverns for hydrogen would need particular geology. So for each hexagon, there would be certain scoring relating to the suitability for different types of infrastructure. Then there are various constraints and opportunities that they look at from a environmental and societal perspective. So, for example, is that land already being used for housing? Is it restricted by, is it a national park, forestry, Ministry of Defence restrictions, etc., that would exclude its potential for energy? Or are there opportunities there for energy infrastructure development? So every one of those hexagons is then given a score from these various criteria that ultimately feeds into the PLEXOS model to tell us how much infrastructure of each type we could potentially develop in each zone of the country. We then run through that in an iterative way. So when we first run the model, the PLEXOS model, the economic model, we would do that with relatively loose land restrictions. And it's going to give us the least cost solution. So for example, solar is generally one of the lower cost technologies that we would have in there as an expansion option, and it would build that out. But then we'd circulate and iterate with our colleagues on the geospatial side. They would then start evaluating what that solar build would mean from a land use perspective, because solar is one of the technologies that has greater land use, greater footprint compared to others. So that starts having implications for agricultural land use, etc. So they evaluate that from a spatial perspective. We also have various stakeholder forums that NESO consults with that also provide their views on the feasibility of different potential pathways. And then all of that feeds back to a refinement of the spatial constraints that we put into the PLEXOS model. So we keep iterating until ultimately we end up with a balanced pathway that is cost-led, spatially optimized, and stakeholder-informed. And that's what we're working towards. So I just wanted to reflect on some of the challenges and innovations that we've faced on this journey producing the SSEP. So for NESO, I think this is one of the first times that NESO has used PLEXOS in capacity expansion mode. And not only just, say, doing generation expansion, but doing networks, interconnectors, co-optimizing of hydrogen. So it is a massive problem to solve. If you're used to solving short-term dispatch problems, daily steps, weekly steps, going from that to trying to solve a 20-year horizon is obviously a huge step up in the problem size. And so we've had lots of consultations, both within NESO and also with external stakeholders, in terms of how to manage the problem size. How do we make it tractable and feasible? There has to be some trade-offs as to the scope of the problem we're trying to solve here. Ultimately, we've ended up with something like 1,000 expansion candidates, and that's actually per year, so there's something like 20,000 expansion decisions that the model is trying to evaluate. Something like 60 million non-zeros in our matrix. That's pushing the boundaries, really, of, I think, what PLEXOS can probably do. We've explored and applied various LT features, rolling horizons, load subtractors, customized sampling, to really make sure that we're sort of solving the problem in the best way that we can. Also like to give a shout out to our colleagues at Energy Exemplar, who have provided their expert advice on the solver settings, so making sure that we really hit the sweet spot for the problem size, and that's been very, very useful. Just thinking about productivity, for those of you that are not using PLEXOS Cloud, it has been a real, I think, game changer for this project. The NESO modeling team themselves are quite dispersed across the country. We've also got external modelers from Baringa and Energy Exemplar involved, and we've all been collaborating seamlessly. So every day, people are making dozens of changes to the master model. We're running that model on the cloud, and that's all happening seamlessly with full version control across that dispersed team. We've got automation on the cloud to take our LT runs, do some transformations and processing, and then kick off ST runs so that we can look at more detailed dispatch operation as well for the 20 years. And then finally, we've developed an automation pipeline around the PLEXOS solution, which looks something like this. So we've got an Azure DevOps pipeline that is used to initiate runs on PLEXOS Cloud. It then extracts results, puts them into a database, and then pushes those out in terms of dashboards to clients, stakeholders within NESO, but also to external stakeholders such as the government and the regulator that have access to a set of views as well. So that was all we had in our canter through the SSEP. We've got plenty of time for questions. There's also links here to the NESO SSEP webpage and the mail address as well. I guess finally, before I hand over to questions, perhaps it's worth saying that we haven't been able to share results today, but the intention is that NESO will be delivering a set of pathways to the government later this year, and then there will be a public consultation on those pathways. So thank you for your time, and we're open to questions.
Hi, just Ali here from Airgrid. Just a quick question on, have you included gas network or hydrogen network constraints into your geospatial modeling part?
So gas and hydrogen network constraints? Yep. So the hydrogen network is very much in scope. So we're having to, well, there isn't one today, but the model is having to build one in order to meet the hydrogen demand projection. And yeah, so we're modeling that hydrogen network. The gas network isn't in scope for this SSEP. It may be in future, but for first iteration, it's not directly in scope, but NESO does have, well, responsibilities and expertise in gas operations. Those colleagues have fed in sort of constraints that we proxy into PLEXOS. So, for example, on gas fleet ramping, we can have that represented in PLEXOS as a constraint. So we're not explicitly modeling the gas network this time, but we're getting some of their feedback in terms of what those constraints might be.
Come in.
Hi, Christian Kaufmann from SSEN Transmission. I wanted to ask about the different pathways, each obviously with different background assumptions that give you an optimal pathway. And then you also mentioned about LT versus ST runs. Do you do some sensitivity analysis, maybe some type of regret analysis, that if you have a certain background pathway chosen, but your outturn assumptions are different, and what that would mean in terms of effective cost or regret of that future against that chosen pathway?
Yeah, sure. So yeah, the themes I showed earlier, they're not necessarily the pathways, they're the levers we're pulling. We're going to have a set of pathways that we're working towards right now, very busy in the modeling team to get those. So they will be an output of technology type capacity out to the future, 2050. Once we have them, we have, I think it's nearly 2 months to do sensitivities on those, to change input costs, build limits. Like there's lots of things we can pull in the model to understand how robust the answer is. So yes, we are checking the robustness of the pathways. Yeah.
Yves Letiès from Google. Thanks a lot for the presentation. Two questions. I think you mentioned at some point that you had like 30 weather years, and so to what extent that was being used for the LT, or is it just for the ST dispatch model? And second question, so when looking at the presentation, the SSEP kind of seems similar to the ISP done by the IMO in Australia. And so to what extent the models and the results would be made publicly available? Like the IMO publishes the PLEXOS model as well as all of the inputs. So to what extent that would be done as well for the SSEP?
Do you want to take the one on weather?
Yeah, so with the weather years, we've tried different approaches. The one we're generally using at the moment is to have a cycle of historical weather years that we work through, rather than repeating the same year every future year. We have also tried stochastically solving for multiple weather year cycles simultaneously, but then that restricts how much sampling we can do. So it's a sort of a balance and a trade-off. And that's all in the LT. And then the ST, as you implied, that it's then possible to, having developed an expansion plan, to then test that against different weather years to check for robustness. We also have colleagues elsewhere in NESO. There's an adequacy team that has a different set of PLEXOS models that do sort of more detailed Monte Carlo simulations of more extreme weather events. And so they are also going to be involved in testing the robustness of the SSP pathways using their modeling data set.
Probably got time for one more quick question.
There was a second part to that
Second
question.
one around, is that, yeah.
Transparency, yeah, sorry. So yeah, there is well, the intention of it is to be as transparent.
Yeah,
but
I think, we can't commit right now, but yeah, we'll take it away, I think, and have a discussion.
The issue there is that the government has supplied a lot of the assumptions to NESO, and so it's for the government to kind of determine, I guess, what can be published when. Sorry, yeah.
Got time for one more.
Hi, Vasco Zaffarina from OffGem, and about the sensitivities and the input assumptions. What is the consultation process for that? Because if you are publishing the pathways, the sensitivities should be done before to test what is the parameters that influence the most the pathways. But if you are doing the sensitivities after creating the pathways, it's kind of not that useful, because you want to test the sensitivity and the uncertainty of the model before, and then you have to open for a consultation. So what is your intent? I guess in this iteration you don't have much time, but in the future iterations, do you think this consultation process is going to be different?
Yeah, so in terms of sensitivities and understanding the inputs and what that does to the outputs, before we started modeling the core pathways themselves, we explored just the exploratory phase in the modeling, that's what we were calling it. Just really understanding what the model really loves building, changing input cost assumptions there to understand at what point would it not build a certain technology type. So we do have a very good understanding of what is sensitive in the model, I would say, even without doing the formal sensitivities on each of the pathways themselves. We were doing them on the base model, if you like. And then as an output, we are going to be producing ranges of technology types rather than just one figure. So again, that should give you a range of capacities for each zone rather than one number. So you can't forecast every single input assumption with 100% confidence. So we'll be able to explain in the pathway options report, how the swings we see on different technology types.
Brilliant, thank you.
Can you take this off now?